Lesson 3.5 is very procedural, and that means we're not going to be learning a new concept. We're just going to be learning new formulas for derivatives and then how to use them to find derivatives of more complicated functions. First rule we've actually already proven before, so I will not take the time in this video to prove this derivative. We've done it before, and that is that the derivative of sine is cosine. So now all you have to do is just memorize that. And we've also proven that the derivative of cosine is equal to negative sine. So again, we're not going to take the time in this video to walk through the limit definition. We've done it before, and we've already seen that derivative of sine is cosine, derivative of cosine is negative sine. Let's just go ahead and use those functions in these other examples. So for example 1, it's asking us to find dy dx for the following functions. If you remember, dy dx is just another notation for the derivative of y with respect to x. So it wants us to find the derivatives of these functions. And what I noticed with this first one here, part A, is that I have a product of x times cosine of x. So I have to use the product rule. So we're going to be putting together all of the rules we've learned thus far into one problem. So product rule says that you have to figure out what your u is. In this case it's x. And your v is, in this case, is cosine of x. And then the derivative of u, or u prime, would be 1, and the derivative of v, or v prime, which we've seen before and which we wrote here, is negative sine of x. And then I'm just going to do u prime v plus v prime u. That was our product rule from section 3.3. So that would be 1 times cosine of x plus v prime, which is negative sine x times x. And so that's just basically cosine x minus x sine x. And that is the derivative of this function here with respect to x. Over here in part B, I notice I have a quotient of two functions, and so that is going to require the use of the quotient rule along with our new derivative formulas. And quotient rule from 3.3 is, again, you have two functions, u, which is the upper function or the high function, and then v, which is the lower function, which in this case is 1 plus sine x. U prime, which we have found is negative sine x, and then v prime would be the derivative of 1, which is 0, plus the derivative of sine x, which is cosine x. And then we're going to do u prime v minus v prime u all over v squared. So that would be u prime v, which is negative sine x times 1 plus sine x, minus v prime u, which would be cosine squared x, because you're multiplying cosine times cosine, all over v squared, which would be 1 plus sine x quantity squared. Now we're done as far as finding the derivative, but we're not done in terms of simplifying our answer, which is an important part. So the rest of the stuff I'm about to do right now is like pre-calculus skills, simplifying trig stuff. First thing I would start with is distributing this sine x. So I'd have negative sine x minus sine squared x, because I have sine x times sine x, and then minus cosine squared x. All of that is being divided by 1 plus sine x quantity squared. Okay, then I notice I have a common factor of negative 1, so I'll just go ahead and factor that out. All over 1 plus sine x quantity squared. Okay, here's where I need you to think back to your trig identities and see if you can locate the identity in this problem. And hopefully you caught it right away. Is we've got sine squared x plus cosine squared x, and that is equal to 1. So we're going to definitely just replace it with 1 because that's much simpler. So then I have negative 1 times sine x plus 1 all over 1 plus sine x quantity squared. And sine x plus 1 is the same thing as 1 plus sine x, so I'm going to cancel out one of the factors in the numerator with one, or the factor in the numerator with one of the factors in the denominator. And so my final answer is negative 1 all over 1 plus sine x. So the thing about the trig functions is not so much finding their individual derivatives and not so much using quotient rule, it's just the simplifying that we have to do after we've done all that. You have to remember your trig identities and be able to factor trig functions and distribute them and things like that. Okay, moving on to our next example is we've got 4 other functions we have to learn the derivatives for, and one of them is tangent. So what we're going to do in this video is we're going to derive this derivative. I'm not going to just tell you what it is, we're going to figure it out, because we're going to remember that tangent is the quotient of sine and cosine. And so what we're going to use is the quotient rule to figure out the derivative of tangent. We'll only do that this one time, and then after we do it once, we're just going to memorize what the answer is. Okay, so then in this case, the u would be sine x, the v would be cosine x. The derivative of u, or u prime, would be the derivative of sine, which is cosine, and v prime is the derivative of cosine, which is negative sine. So then I'll go ahead and do u prime v minus v prime u all over v squared. So u prime v is going to be cosine squared x, because it's cosine times cosine. V prime u would be negative sine squared x, so we're going to do minus negative sine squared x all over v squared, which is cosine squared x. Then we're going to go ahead and cancel out that double negative right there, which turns it into cosine squared plus sine squared, which we just reminded ourselves in the last example is equal to 1. So then this whole derivative turns into 1 over cosine squared x, which hopefully you remember that's the same thing as secant squared x. So the derivative of tangent is secant squared x. I derived it here so that you can see where the formula came from. However, that's not how I'm going to expect you to find the derivative of tangent. I'd rather you just memorize this formula, because as you'll see, finding the derivative of one trig function is going to be a small part of a much larger problem, and we are not going to have time to derive this every time. It's best just to memorize it. However, if you do blank, you could always, walk through these steps to get the answer. Okay, and then the derivative for cotangent, if I did a similar process, which I will skip here because you're actually going to do that in your homework, but you would set up the quotient for cotan, which is just the reciprocal of tangent, so it'd be cosine over sine, and then you would do the same process. And when you do that, you end up with negative cosecant squared x. So I also would like you to memorize this formula. Then that brings us to our secant and our cosecant functions. So the derivative for secant, we're going to also use the quotient rule to find that. Because if you recall, secant is simply 1 over cosine. And so that is a quotient, so I'm going to go ahead and use quotient rule, where the u would equal 1 and the v would equal cosine of x. So then the u prime would simply be 0 because the derivative of any constant is 0, and the v prime would be negative sine of x. So then I'm going to take that up here. We're going to go ahead and do u prime v minus v prime u all over v squared. So that would be 0 times cosine x minus negative sine x times 1 all over v squared, which is cosine squared x. Well, 0 times anything, that's just 0. And then again, here we have a double negative. We will make that positive. And so I end up with sine of x all over cosine squared x. Now for the purposes of stating the answer for this derivative, we're going to split that into 1 over cosine x times sine x over cosine x, because that would still give us a sine x in the numerator and a cosine squared x in the denominator. But now we can see the two functions this consists of. 1 over cosine x is simply secant x. Sine over cosine x is simply tan x, and we're multiplying them, so the derivative of secant x is simply the product of secant x and tan x. That, again, is the formula that we are going to memorize. We derived it here, but now I would like you to simply memorize it. Similarly, if I were to find the derivative for cosecant, I would do a similar process where I would put 1 over sine x, because that's what cosecant x is equivalent to, and then I would use the quotient rule and then walk through the similar series of steps. If you do that, you would end up with negative cosecant x times cotangent x. You actually will be doing that in your homework. You'll be asked to derive this formula. But for applications of it, or just future problems, I would rather you simply memorize it, because again, you're going to need to just call upon it quickly. You won't necessarily have time to derive it. So here's an example of what I mean. This question is seemingly very harmless, but it's going to turn out to be quite challenging, as you're going to find out in a second. This is asking us to find the equation of the line. So don't forget, at the end of the day, I need to have something that looks like this. Point slope form. That's my answer to this question. I just have to figure out what the slope is and what the point is. So we're finding the equation of the line normal to the graph of y equals tan x over x at, this is important, x equaling pi over 4. Maybe the first thing that I'll go ahead and find would be the point. So I have to know what the y value is at pi over 4. I know my x coordinate is going to be pi over 4. What I need to figure out is what y is equal to when you evaluate it at pi over 4. So I'll go ahead and take the expression for y, and I will evaluate that at pi over 4. Tangent of pi over 4 is 1, and then I'm dividing that by pi over 4. So you multiply by the reciprocal and you get 4 over pi. So I know that my point is equal to pi over 4, comma 4 over pi. Now for the hard part. We need to find the slope. So what we need to remember is that the normal line is perpendicular to the tangent line, so if you could write that for yourself. The normal line is perpendicular to the tangent line, so I need to find a slope. So my m is going to be perpendicular to the derivative of this evaluated at pi over 4. So it's going to be perpendicular to dy dx evaluated at pi over 4. Okay, so let's go ahead and find what that dy dx is going to be. So I know that I'm going to have to use quotient rule because I have a quotient of two functions. So my u is going to be tan x and my v is going to be x. My u prime is going to be secant squared x, and my v prime is going to be simply 1, since the derivative of x is 1. Then we'll go ahead and do u prime v minus v prime u all over v squared. U prime v would be x times secant squared x, minus v prime u would be 1 times tan x, all over v squared, which would be x squared. Now for the fun part, which is plugging in the pi over 4. So that would equal pi over 4 for x times secant squared of pi over 4 minus tangent of pi over 4, all divided by pi over 4 squared. I'm going to do some scratch work over here off to the side. So secant of pi over 4, if you recall, is equal to rad 2. Tangent of pi over 4, if you recall, is equal to 1. So I'm going to go ahead and swap those values out for secant and tangent. And so that would give me pi over 4 times rad 2 squared minus 1 all over, and then pi over 4 squared would be pi squared over 4 squared. which would be pi squared all over 16. Okay, so I'm going to have to move this over here. So then this just turns into 2. The square root of 2 squared is just 2. So I'm going to have 2 pi over 4 minus 1 all over pi squared over 16. Then, just to make it simpler, I'll multiply the whole numerator by 16 and then the whole denominator by 16, which is okay because really all I multiplied by was 16 over 16, which is 1. So then that would give me, when this distributes here, the 4 cancels out and I'm left with 4 times 2, which would be 8 pi minus 16 all over pi squared. So that right there is the slope of the tangent line. So this thing right here is equal to slope of the tangent line. But what I needed to find was the slope of the normal line. So if I flip this over and change the sign, that would give me the slope of the normal line. So if I had negative pi squared all divided by 8 pi minus 16, that is the normal slope right there. And that's what I'm going to use in my answer. So if you can follow me back to the top here, my final answer is I'm going to take out the y1 and replace it with the 4 over pi that we found earlier. I'm going to take out the slope, m, and replace that with this number here, the negative pi squared over 8 pi minus 16. Because that's the slope of the normal line. And then last but not least, x1, that was pi over 4. That was the x-coordinate of our point. And so that is finally the answer to this question. So you can see there was a lot going on there. Even if you look at the work, it just looks crazy. We had to find the point on the graph by plugging pi over 4 into the original function. We had to find the slope of the tangent line by taking the derivative, which was quite a long process of quotient rule, knowing the derivatives of the trig functions, evaluating trig functions at pi over 4, simplifying that number. That was only the slope of the tangent line. Then I had to flip that over, change the sign to make it the normal slope. Then I had to go back to this equation of the line and then plug everything into the right place. So you can see that these questions can become quite complicated rather quickly. Okay, then we're going to end this segment with one last example, putting together the concepts of 3.4 and 3.5, which is motion. So let's suppose we have an object moving along a horizontal line according to this function, y equals cosecant x. Whoops, I have a t there. Where x is in seconds, it's the time in seconds, and it's between 0 and pi, and y is measured in feet. The question is asking, what is the velocity of the time of the function, at time x equals pi over 4? So I shouldn't say function, I should say object. What is the velocity of the object at time x equals pi over 4? So if you remember, velocity is just the derivative of position. And so I'm basically just going to find dy dx. So y is equal to cosecant x, and then we learned earlier that the derivative of cosecant x is negative cosecant x cotan x. That would be the velocity at time x. I want to find the velocity at time pi over 4. So I'm going to evaluate that at pi over 4. So I have negative cosecant of pi over 4 times cotangent of pi over 4. Cosecant of pi over 4 is rad 2, and cotangent of pi over 4 is 1. So this would become negative rad 2 times 1. And so that's negative rad 2 feet per second. Change in distance over change in time. Feet per second. So that's our velocity, finding the derivative of position evaluated at the time in question, which was pi over 4 seconds. Part B is asking for the acceleration. And if you recall, acceleration is the derivative of velocity. That's the v prime t, or in this case, v prime x. So we're going to find the derivative of this function here. So velocity was negative cosecant x times cotan x. So we're going to have to use the quotient rule because this is a quotient of two functions. So that is, I'm sorry, not a quotient, excuse me, product rule. We're going to use the product rule because it's a product of two functions. So in this scenario, the u would equal negative cosecant x, and then the v would equal cotan x. We learned those derivatives today as well. Let me make some room here. U prime is going to equal positive cosecant x cotan x, and v prime is going to equal negative cosecant squared x. Then I just have to do u prime v plus v prime u. So maybe I'll do that down here. So u prime v would be cosecant x cotan x times cotan x. So it would be, so I'm going to do v prime x equals cosecant x cotangent squared x plus v prime u, so these negatives are going to cancel out, and I'll have cosecant to the third x, because I had cosecant squared times one more cosecant, that would mean cosecant to the third. But then I have to evaluate that at pi over 4, and so cosecant x is rad 2, cosecant of pi over 4 is rad 2, cotangent of pi over 4 is 1, and it's squared. And then I have another rad 2 to the third power. So then this part is rad 2, and then this part is 2 rad 2. And so I end up with a total of 3 rad 2. And since that is acceleration, or it's the change in velocity over change in time, it'd be feet per second per second. So it's feet per second squared. 3 rad 2 feet per second squared. Okay, then part C is asking whether or not this object is speeding up or slowing down at time t equals pi over 4. And it looks like it would be slowing down because the velocity is negative but the acceleration is positive, meaning they have opposite signs. So it's actually slowing down at x equals pi over 4 because velocity and acceleration have opposite signs. Then one last little thing you need to know that is included in 3.5 in our book is just this matter of jerk right there. And that is the rate at which acceleration is changing. So basically it's the derivative of acceleration. So jerk, which equals, I guess, j of t, that would be a prime of t, the derivative of acceleration. And so that makes it the third derivative of position. So in this example, the one that we just did, the jerk would be the third derivative of y, which I'm not going to find here because I don't even have the room, but it would be the third derivative of this position function up here. And the units would be, in this example, it'd be feet per second squared per second, which is feet per second cubed. That concludes our lesson on 3.5. I will see you in class.